Okay, chapter 3, we're going to start talking about exponential functions. So we have this function f of x is equal to b to the x, or we could be writing it as y equals b to the x, where b is some positive value. B cannot be 1, so it has to be some positive value other than 1, and x can be any real number. Okay, and these are what we call exponential functions because the variable is in the exponent. So let's look at the graph of the function of f of x equals 2 to the x. So we're going to make a table of values here. So when x is negative 2, that means we're going to have 2 to the negative 2 power, which really means 1 over 2 squared, which is 1/4. If x is negative 1, that would be 2 to the negative 1 power, which is 1/2. When x is 0, anything raised to the 0 power is just 1. 2 to the first power would be 2, 2 to the second power would be 4, and 2 to the third power would be 2 times 2, which is 4, times 2 again, which is 8. So if we plot some of those points, negative 2 1/4, maybe down in here somewhere, negative 1 and 1/2, just a little bit higher, 0 1, okay, 1 2, then 2 4. Notice how fast the graph is increasing. At 3, I'm all the way up to 8. Okay, so notice how quickly this graph is growing. Okay, and notice here we have our y-intercept at 0 1, and that's going to be the case for any exponential function. They're all going to pass through that 0 1. Okay. Look at another graph, 1/2 to the x. Okay, so when x is negative 3, that means I'm really looking at 1/2 raised to the negative 3, which the negative, remember, the negative exponent means I'm going to take the reciprocal, so that really means the same thing as 2 to the third. That's going to give me 8. 1/2 to the negative 2 means 1 over 1/2 squared, which is going to give me 4. 2. Again, anything to the 0 is 1. 1/2 to the first would be 1/2. 1/2 to the second would be 1/4. 1/8. Okay? So if we go through and we plot those points again, you can see negative 3 8 up here. Negative 2 4. We've got negative 1 2. Again, 0 1, like we mentioned before. These exponentials are going to go through 0 1. And then at 1, I'm sliding down to 1/2. 2 is down to 1/4. 3 is down to 1/8. Okay, so that graph is coming down here, and now it's starting to flatten out, and it's approaching that x-axis. Okay. So this is the graph of f of x equals 1/2 raised to the x power. Okay. So here's some characteristics, and a couple of those we saw in those two graphs, some characteristics for exponential functions. Okay. First being that the domain is negative infinity to infinity. Okay. The range is going to be 0 to infinity. So I can put any value I want in for x. My outputs are always going to be positive. Okay. Here in number 2, I mentioned this, that the graph of any exponential function is always going to pass through the point 0 1, because anything raised to the 0 power is going to be 1. So therefore our y-intercept is going to be 1, and there is no x-intercept. You notice that I never cross the x-axis in either of those two graphs. Okay. If the base of my exponential, my v-value, is greater than 1, then the graph is going to be increasing. It's going to be rising as it goes to the right. Okay, so as we see right here. If the value of b is between 0 and 1, it's some fraction like we saw in the 1/2, then that graph is going to be decreasing. Okay, right here, f of x equals b to the x, where b is between 0 and 1. When I'm taking a fraction as my base, my function is going to decrease. It's going to continue to get closer and closer to the x-axis. Exponential functions are one-to-one, which means that they do have an inverse. They pass the horizontal line test. Okay? And those exponential functions always approach the x-axis, which means, as we saw at the end of first semester, we have a horizontal asymptote at y equals 0. Okay, so those are just a few of the basic characteristics of these exponential functions. Now, we have what's called the natural base of e. Okay, e is one of those special numbers in mathematics, and e is actually the value of taking 1 plus 1 over n and then raising that to the n power. And as n gets larger and larger, as n goes to infinity, then the value of this whole quantity here gets closer and closer to what we call the natural base of e. Okay, it's approximately like 2.718, and there's some more numbers back there, but that's kind of the approximation that we use. Okay, so if you think of it in terms of calculus, this is kind of a precursor to calculus. We call that a limit. Okay, so when we talk about this here, this is really representing the limit. So the limit of this sum, this exponential here, as n goes to infinity, as n keeps getting larger and larger, this value here will continue to get closer and closer, and will approach this value of e, this 2.718. And it's irrational, so there's some more numbers back there, but you kind of get the general idea. So a little glimpse into calculus, and it's hopefully down the road for you. Okay. So one of the things that we do with exponentials is we have some formulas for compounding interest. Okay, and there's one formula which talks about compounding interest a certain number of times per year, which is this first one. We have P is the principal, that's the amount that was initially invested. Okay, so this is your initial amount. Sometimes you'll see it called A0, A0 for your initial amount. N is the number of compoundings per year, how many times you're going to compound the interest per year. The R is the rate. Okay, we've got that down here at the bottom. R is the interest rate. Okay, and T is the time in years. Okay. For continuous compounding, where that interest is building all the time, you're not just going to compound it every so often, you're going to do it all the time. Then we go to this simpler version, which uses the base of E, that natural base, where you take the principal, the initial amount, and you multiply that by e raised to the RT power. So that exponential with the natural base of e. So those are two formulas that are used for compounding interest. All right, so we're going to make an investment of $8,000 for 6 years. We've got two choices between the accounts. One is going to pay us 7% per year compounded monthly, and the second is 6.85% compounded continuously. So we want to see which investment is the better option, which one's going to make us more money. Okay? So if we're compounding it monthly, we've got 7%, and N is going to be 12, and T is going to be 6. So the amount of money we're going to have is the principal, the 8,000, times 1 plus, the rate is 7%, so 700ths, divided by 12, raised to 12 times 6. So when we calculate all that out, we've got $12,160.84. Okay. If we look at compounding it continuously, then the amount is the principal times e raised to the rate, which is 0.685 times 6. Okay. So computing that, we end up with that amount being $12,066.60. So we can see that the better investment is going to be the 7%, the 7% compounded monthly. That's the one that's going to make us the most money. Okay? So an example of how we can apply these exponential type functions to some real world application to see which sort of investment is going to give us the most bang for our buck, which one's going to make us the most money. All right, so for tomorrow, I would like you to do these 5 problems. Okay? and we'll go over these. I will either come around and check them or collect them at the beginning of class. I haven't decided that yet, so make sure you do them on a separate sheet of paper in your notebook in case I decide to go ahead and collect those. So I want you to do these 5 problems. They relate exactly to the same types of problems that we were doing in the examples. And then we will work on some more of these types of problems in class tomorrow. We'll see you then.